All right, welcome back, everybody. We are now ready to move into Chapter 2. And if you watched the classification of ODE's video, then you know where we are starting. We are going to go ahead and start with first order differential equations, right? Remember that, so for those of us who didn't watch it, first order, like the order of a differential equation, just tells you the number of derivatives, the highest number of derivatives that you must compute for a differential equation. So we'll talk about that in a moment. But to give you some context of where we're going, the things that we are looking for when we try to come up with a solution for a differential equation is we would like to know, first of all, whether or not that solution even exists. Right? So if I have a general ODE, I may or may not be guaranteed a solution exists. And even if it does exist, can you tell me anything about its solution space, right? The domain over which it is defined. And can you tell me which solution spaces it can exist over? Or is there some sort of exclusion in the domain that we don't know about just by looking at the differential equation, which may or may not be the case? And if we have a solution, we would like to know, is it the only solution to the differential equation? Right? We saw in our one of our previous videos that there can be a general solution, that there may be infinitely many solutions to a differential equation. But if we identify an initial condition, then we might be able to pin down exactly one solution. So maybe there is one solution to a differential equation. And what conditions do we need in order to guarantee that uniqueness? Right? Does it have to be a specific location or a specific point that we need to pass through? Or can I just tell you an arbitrary list of conditions that this function has to satisfy? Will that hamper the existence of the solution? There are lots of considerations that we have to make. And more from a practicality standpoint, we'd like to know whether or not we can actually compute the damn thing. So if there is an explicit solution, is it possible to determine what that solution looks like? Right, sure, we can write down an integral for what a solution might look like, but can we actually compute the antiderivative? Or do we have to resort to a numerical simulation? Or maybe the solution can be represented just not through elementary functions. So there are a lot of considerations we have to make as we go forward in our study of differential equations. And I'll just give you one quick note from our last video. This last equation in the classification video, this is the famous Navier-Stokes equation. It is a first-order equation, so by what we talked about last time, this should be a relatively easy differential equation to solve. But this guy is very non-linear. And this is actually what kills our ability to solve this guy explicitly. We actually don't know if there is a solution to this differential equation, this system of PDEs, as it were. We don't know if there's a general solution. And for specific initial conditions, we really don't know. And it's supposed to be a first-order equation. It's supposed to be really easy, but the nonlinearity really messes with this. Also, I have no idea why it says second order in the notes. It should say, oh, the battery is low, apparently. This is a first order system. So I found another typo in my notes. Yay. Yeah, so this is like the whole spiel here is that there are certain things that we need to figure out first. Right? There are goals in mind when we try to solve differential equations. So let's go ahead and say that this is its own video, and then we'll go ahead and start chapter 2 in the next video. So the takeaway here is that there oftentimes will be solutions that we can compute. And that's usually because we've made it so we can compute these solutions. We know what kinds of differential equations have solutions, and we know how to make them easy to find, or we know how to build models that have easily attainable solutions. But for an arbitrary equation, odds are you have no explicit solution. Odds are its existence is unknown. Odds are it's you don't know about its uniqueness. You don't know if you even have a solution. You don't know if it's the only one. And far from both of these, we don't know if we can compute these solutions in general. So it's kind of a bleak outlook. But what we do instead, to kind of give ourselves the best shot of understanding these differential equations, is kind of what we did earlier with our slope field representations of solutions. We like to use numerical simulations to figure out if we even have a solution. And if it does, what does it look, if we do, what does it look like? Excuse me. So if you feel like checking out some numerical simulations or numerical approximations of solutions to ODEs, excuse me, then I highly recommend that you check out, usually in your university, there's going to be a course called Numerical Analysis or Numerical Methods. And this is, part of those courses is you talk about how to solve ODEs or PDEs numerically. Like if you can't solve it by hand, then you go ahead and pop it into a computer and see what it approximates. And I highly, highly recommend these classes. They're some of the most practical math that you will ever study. So maybe I'll make a playlist about this class as well. So go ahead and tell me in the comments if you'd like to see a playlist about numerical analysis, and specifically if we're going to solve some ODEs numerically. I think that'd be kind of cool.